All right, so good morning. I'm going to present about spacesuit systems. Thermal control actually is a big issue. What you see here in this picture is a number of spacesuit hard upper torsos where they are stored while they are not used. The thing is, and that was a challenge which proliferated throughout the entire space shuttle program, for example, is that you had marvelous technology, but once you get it back from space, you had a long list of things to do before they were requalified for flying again. So you wouldn't just store them in the corner and then take up again, but actually refurbishing such a spacesuit will take weeks and weeks and weeks. You would go through binders about that thickness, 3 of those, to actually pull every switch and recreate every conceivable conditions to recertify them again. And so the reusability of the suits, it was given, but only for a short amount of time. So if you look into the ratio between maintenance time versus preparation time, post and pre-EVA, versus the actual EVA time, these are bad numbers. You have only short amount of hours versus a long preparation time. Now the problem with this is if you take this to Mars, you don't have the time for doing a servicing of a spacecraft for weeks and weeks and weeks. You want to go out the next week again. The level of reliability, of robustness you have to take into account when building a spacesuit for Mars is very different. Let's see what the Russians did. The Russians always had a very pragmatic approach to spacesuit design, and they actually had started their first pressurized suit systems already in the late 40s, just after the Second World War, when the first high-performance, high-altitude fighter planes were developed. The idea for the Russians was that you have, of course, the same environment, but the approach of getting into a suit in a fast way, have it at low maintenance capability. That's something where the Russians were really good. They learned a lot in the first EVAs. I mean, if you look into the EVA of Leonov, Alexander Leonov, the first Russian to walk outside, that was pretty scary, because what happened was the spacecraft was so small they couldn't afford an entire airlock inside. So they had to have an inflatable airlock, which looks like an inflatable tube, where you open the door on the inside, you go into the tube, you close the inner side, you open the other side, then you're out. That's what he did. And he was hanging on the umbilical. And what happened was that once he tried to get back after his short EVA, he realized, oh my gosh, I'm too fat, because it was inflating so much, he couldn't make it back to the airlock anymore. And the second thing was, he was out of comms range. He wasn't able to talk to Moscow anymore. So what are you going to do? You are in orbit, you're running out of air, you're running out of EVA time, you have to go back, you cannot do it because you have too much air in your suit. What he did was basically something which is totally unimaginable nowadays, and that is go to the pressure valve and release pressure from your own suit while you're on an EVA. It was going down to barely 0.2 bars, basically, to get slim enough to make it back in the airlock and make it safely back to the spacecraft. That was a near hit. He almost died there. That's something you probably want to never can imagine happening nowadays anymore. The current system which is used is the Orlan, the Eagle system, Orlan M, which has, by the way, a little bit of European heritage to the EVA 2000 suit as well. The Orlan suit system is a rear entry suit system. Like the American system, the shuttle in ISS EMO, you have a hard upper torso, like you would be a medieval knight or so, where you put it on basically and put on the trousers and put on the gloves and that's it. For the Russians, they said it's much faster if you just open the back and you step in from the behind, which you see here now in the image. This is a rare image of an open PLSS. The communicating to the public an image, a photo of an open personal life support system is a very intimate look into your design studies, so to say. So usually you have a curtain where you don't see anything yet. There are hardly any pictures around from the Chinese 5-ton suit, for example, which is based upon the Orlan design originally. Now, what you see here tells us a lot, because it gives you an impression of the sizing, the volumes of the oxygen containers, the battery packs, for example, the lithium hydroxide, which is absorbing the CO2. That's one of the few consumables of the spacesuit which you have to exchange after EVA, because it has been absorbing the CO2 of the astronaut or the cosmonaut in this time. The cool thing about this is that it is a single-person donning system, which means you step in from the back with your underwear on, with all the tubes where you have the cooling liquid circulating, and you get into it, and then you have a lever on the back side which helps to close the PLSS to seal it actually, and here you go. So a little bit simplified. But in general, the donning time for the Russian Orlan is much less than for the shuttle EMO, for example. Also, the pre-breathing is very different. Now, pre-breathing, what's that? One of the risks we have, once we lower down the pressure, and every diver knows that challenge is, the amount of nitrogen which is solved in your blood is likely to perform as an outgassing if you have a reduction of the ambient pressure. Now that's a problem because if you have outgassing nitrogen bubbles in your blood, that can lead to blocking of blood vessels. It can even lead to like heart attack-like symptoms. It can lead to outgassing of nerves in the spinal cord. You can get paralyzed. You can die. That's simple decompression sickness, so to say. Now you can remedy this a little bit by taking aspirin just before you go out on the suit. So the astronaut always take 375 milligrams of aspirin before going in EVA. But still there's a residual risk. So what you do is you try to wash out as much nitrogen as you can, which means you do the pre-breathing. We used to call this the camp out. Camp out means that before the actual EVA, like on the ISS, the astronauts who are going on EVA, they are taking a breathing mask with pure oxygen, strap it on their head, and keep it on for the next 12 hours. That's the reason why they call it camp out. So they sleep actually in the airlock with 100% oxygen to wash out the nitrogen. But this, as you can imagine, is a very tedious process because those 12 hours, they can not do a lot because they are only preparing for the EVA. They can do prepare the suit or so, but they cannot do anything else. So we've looked into ways how to reduce the pre-breathing time, and there are shortened protocols now which are now becoming the standard that you can actually, they don't have to do a 12-hour camp out procedure, but you can have a certain pressure versus oxygen concentration protocol which helps you to avoid this decompression sickness anymore. So we are now talking about only a few hours of preparation time in total anymore, including all the mechanical setup of the suits or so, but still going out on a spacewalk is nothing you do on a spontaneous basis. You really have to plan for it very, very diligently. One of the major differences between the US system and the Russian system up to now is the pressure level. Now we said the more pressure you have in the suit, the more cumbersome it is to work with. On the other hand, if you want to breathe, you have to have enough oxygen. So you in theory, you could go down to like 0.2 bar as long as you have 100% oxygen atmosphere, as opposed to the rest being filled up with nitrogen. Now the problem is that if you have 100% oxygen atmosphere, things get really nasty from the safety point of view. And I know a colleague of mine who's been working on the EVA 2000 suit of the European Space Agency. He said they had a model pressurized at 100% oxygen at 0.2 bar. And what happened was that they had to forget to degrade one of the pipes, which were the high pressure valves for the pressure part of the system. So they were having microscopic little filaments of steel pointing towards the airstream. And at those pressures, this was before you go to the 0.2 bar, that's about the 200 bar or even more, at high stream, this gets ignited. So they were almost killing a suit technician by lighting him up because of this little mistake they had made. So we really have to respect that. So since the Apollo 1 fire, where also the 100% oxygen atmosphere caused the disaster, we know it's not a good idea to work with 100%. So where's threshold? Where should you go? And that's almost a quasi-religious discussion, which is the perfect pressure. The Russians go for 38 kilopascal. And the Americans go for a little bit of a higher pressure. The reason for going for higher pressure is that the camp out is shorter because the pressure differential is a little bit less. The advantage of the lower pressure is you have more mobility. And it's a question of where are your priorities, so to say. So for a typical Russian Orlan M suit, right, which is one of the current versions upgrading right now, but it's the current one which we use right now, is that you have oxygen inside with like 41 megapascal. In the 2-liter bottle, we have regulators which monitor the suit pressure and feed additional oxygen when needed. Again, remember, no spacecraft, no spacesuit is really airtight. And it also has an emergency activation just in case of a rapid pressure loss that you have, even if you have a micrometeorite hit of like a few millimeters bolide or so, you would be able to survive for like another, at least tens of minutes, which should be enough to get you back safely into the airlock. But remember, nothing is airtight. You always have to compensate for the losses you have in the suit themselves. I think the interesting thing for the space suits from engineering point of view is below the surface. So how do you do the ventilation, the regeneration, and above all, the thermal control system? Because if you kind of think of it, if you're standing on the moon in the sunlight, and the sunlight you have like plus 120 degrees Celsius, you would burn on one side, you would be freezing on the other side because there's no atmosphere around you which would basically equalize the temperatures. Now the idea is that you have to mimic this with the liquid cooling and ventilation garment, which means you have a circulating fluid in your underwear, which helps you to maintain this balance, so to say. At the same time, you have to remove dust and contaminants. You have to remove the CO2. This, again, mostly is done with the lithium hydroxide. You have to regenerate the air. You have to get rid of the odors. You can imagine 6 hours in a suit and not being able to open a window for getting some fresh air. You can imagine what it smells once you get back, and I know what I'm talking about. And so after each EVA, there are a few consumables which you have to replace. Now for the thermal control, that's a tricky thing, because the human body, depending on the workload you put on him, is a pretty good heat producer. I mean, having like 200-300 watts produced up to like 600 watts is real in the heavy loader, so that's not uncommon, which means if you have a perfectly isolated system, even at minus 100 degrees outside, you would overheat. And that's something most people don't realize, that even if you're standing on the surface of Mars at minus 70 degrees Celsius, average temperature, you would say, well, we have to heat him. No, you don't have to. You have to get rid of the heat. And that's a non-trivial task. On the one hand, of course, you can try to keep as much heat off as possible. That's the passive system. That's the insulation which reflects the external heat and contains the internal heat. Yeah? And then there's an active part which you need as heat exchanger to remove the body heat. Now there are a few ways how to do this. First of all, you can radiate heat. That's not super efficient. You can have just a heat exchange with the ambient air, which you don't have in orbit, of course, which you have to some extent on Mars. But in vacuum, that just doesn't work plainly. So the way you do this is with a sublimation process, which means you have a water or a fluid, a non-toxic fluid obviously, which you have in the liquid cooling and ventilation garment, which you put over basically a metal plate with many holes in it. And so once those tiny water droplets go through this porous membrane and they are exposed on the vacuum on the other side and the heat exchanger on the one side, the vacuum causes then the water to freeze as a microscopically thin sheet of ice. The heat from the heat exchanger combined with the pressure differential in the vacuum of space cause the ice then to sublimate. So if you freeze it, then you sublimate it directly into vapor. And the large amounts of heat are absorbed by the water during the sublimation process, and so you have to replenish the water. So a shuttle EMO is constantly losing water through a soft tank and needs to be refilled between the EVAs. That's a very clever system, very efficient system. Actually, I even brought a picture of the Apollo sublimator, where I actually see in the upper part of the image this porous membrane where you put over the water on the one side and it's going out on the other side, so basically. Problem is, on Mars it doesn't work. And that's the bad news, because as I said, there's a little bit of pressure on Mars. You typically have roughly between 9 to 11 millibars as a typical air pressure there. Now, for the sublimator to work, you really need vacuum on the other side. With like starting at 3-4 millibars already, this system gets incredibly inefficient. So the theoretical value would be 6 millibars. The actual value which has been tested with the best sublimation coolings we have right now is 4.5 millibars. So that's already beyond what Mars offers. So sublimation cooling would not work for Mars, and that's a big issue. Because on the other hand, again, radiation is not very efficient. Circulation with direct air contact is also not very efficient because of the little air pressure, so to say. On the other hand, you cannot even like sweat it out because of planetary protection issues. So the thermal control system for a Martian spacesuit is something we don't have yet. See, one thing you have to work on. There have been a few ideas. One of them was that you have a heat concentration, that you have like little wing-like structures or radiators basically where you concentrate the heat to make them really super hot, that like 600 degrees hotter or so, then the radiation becomes efficient or so. But again, that's not a very elegant system, and first of all you have to have again the energy to concentrate the heat as well. So it's a catch-22 in a way, mostly worsened by the planetary protection issues, so to say. Mass, that's a biggie, the best sense of the word. The thing is, the current shuttle EMUs or ISS EMUs, they weigh, depending on the configuration, in the order of 120 to 140 kilograms, in that order of magnitude. On Mars, you have lower gravity, of course, but still it trickles down to at least like 40, 50 kilograms of you would need for a Martian spacesuit, so to say. So right now, if you would take a shuttle or ISS EMU and put it on Mars, it just wouldn't be the right thing to do. It's not made for walking. Yeah? It has operating cycles of 12 or less or so. It has atmospheric pressure inside, which is not good for Mars. So there's a lot of catch-22s which would block you from actually putting a suit on Mars. And as the last part to this first segment now is that suits are always embedded in a system of systems. You have interfaces to the spacecraft itself, you have interfaces to tools, to vehicles, to rovers, to mobilities, to geological tools, and so on. So the spacesuit of the future, as opposed to the Apollo spacesuit, must be able to communicate with those tools as well. Just mentioning here the Internet of Things, we've realized this many years ago and implementing this as well. So to sum it up, why wouldn't ISS EMUs work on Mars? So first of all, the multi-layer insulation wouldn't protect against thermal radiation on Mars. Yeah, the sublimation cooling would not be working as well. All the current and previous designs for EMUs are out of range in terms of the mass budgets to be able to walk on Mars. So we are hoping for mass reductions for at least 50% or so. But still, you need pressurized suits on Mars, of course. Huh? So you would need a fresh approach. But there are also a few good news for suits on Mars. And just let me give you a few provocative thoughts on that. First of all, cold sink temperatures are available for heat rejection to ground by radiation, which means just imagine concentrating the heat in the boots, in the soles. You have some nice shoe heating as well, but once you step on the cold ground, you have already something which is going to consume up the heat, for example. You have a range of minus 140 degrees to plus 30 degrees, or let's say plus 20 degrees in the order of magnitude, which means the amount of the temperature range you have is much more benign than you would have on low Earth orbit, for example. Convection heat loss is conceivable. Now I said the air pressure is very low, but you can force it down by forced convection with a fan system, for example. Then micrometeorite danger is literally non-existent due to the little atmosphere. Yeah? You have a lower risk of galactic cosmic radiation events, for example. The solar flux is less. You have latitude variation. So by choosing where to land on Mars, you can choose the thermal environment. So why not consider, like we do on Earth, that you have a winter garment and a summer garment, like we do on Earth. When in winter I wear different things than I do in summer, for example. Then of course you have gradual temperature change. They're not as harsh, the gradients are much more benign than you would have in low Earth orbit. Then you have carbon dioxide in the atmosphere. So carbon dioxide contains oxygen. So if you're able to process the Martian atmosphere, you wouldn't need so many oxygen containers with you, which again would lower down the mass penalty, of course. So you can use also the carbon dioxide to pressurize the suit. I mean, not for the breathing air, obviously, but for pressurizing the suit, you could use CO2. It's all out there. You just have to suck it in, basically. The Mars atmosphere contains a little bit of water, not much. So the amount of precipitable water in the Martian atmosphere is below than like 10 microns or so. But still, you could distill it in some way. And of course, you might also land in areas where they have soil permafrost with water. So there are water resources which are not available in low Earth orbit, obviously. So there are a few things, if you use the environment in a clever way, like we do here on Earth, you might even have a better starting point than for free EVAs. What about the future? There's a lot of concepts out there. Right now, there are 4 teams worldwide which are working on spacesuit design, system design for Mars exploration, for example. And we in the Austrian Space Forum are the only group in Europe right now doing this. Now, you have to differentiate between various approaches. First of all, there's something we call the volumetric models, where you have a general impression in terms of the mass and the sizing of the suit, but the functionalities are very limited. On the other hand, there are clever design ideas out there which are yet quite far away from the implementation and getting them space qualified. However, I'd like to share with you a couple of those where we might see something evolving in the near future which is maybe not really revolutionary, but really a game changer to some extent from the engineering point of view. Let me start with the one thing you're all going to stumble across if you look into future concepts, and that's the biosuit. Biosuit is a system which originally was derived in the late 60s, the Leotard suit by Dr. Webb, where the idea would be that you could eliminate the one very uncomfortable layer, and that's the air layer in the spacesuit. Which means you're basically dressed in something you would call, like a leggings or so, very tight, looks very like shapewear kind of suit, and that you are able to maintain a pressure because the human skin is an excellent pressure container. And as long as you can constrain that with that very suit, you don't need a pressure layer in between. So that looks very promising. So you see a picture of Dr. Webb, the father of those skin suits, basically in the late 60s. This idea somewhat got lost in history. It was picked up a few decades afterwards by Professor David Newman, who is now an associate administrator at NASA, with the biosuit, or it's also called the skin suit, or the MCP, which stands for Mechanical Counter Pressure Suit. And the idea is that you overcome one major limitation challenges a normal spandex suit would have, because that means once you're folding an elbow, for example, you are creating ripples. And those ripples are, again, containing maybe some air, so the system wouldn't work if it just have a tight overall, so to say. The idea, the concept behind this is that no matter how you move your joint, there are always so-called lines of non-extension. And those lines of non-extension, they can be mathematically modeled and then give you the position of the seams where you have to put the spandex suit into. And even if you move your joint, the lines of non-extension do not move at all, or they do not get expanded, so to say. This is a non-trivial task from a mathematics point of view, but it works out, and so we have, the MIT group has already made experimental versions of this for the simple joints. Simple joints means you have 1 or maybe 2 degrees of freedom, like the knee, for example. Now for other parts, like the torso rotation or so, or a shoulder rotation, things get really nasty and complicated. But this is a great starting point where you could be able to contain the skin within this pressure vessel. So, however, it comes at a price, as always. And coming at a price means that you have a constant mechanical pressure on the skin. By definition, that's the way the MCP works or so. The problem with this is from a medical point of view, and we've flown a few systems which are similar to this kind of MCP suits on parabolic flights, for example, and what we realized, even after short amounts of time, there are pressure damages available to the skin. And if you do this over several of hours, even while moving or so, this really might lead to major skin damage as well. Then, of course, one of the major advantages the MCP suit has, and that is you being able to sweat through the suit. So you can do the same thermal control system like you would have for a human just in ambient air. And it's very elegant because if you heat it up, you sweat it outside the MCP suit, and here we go. The problem is, from an astrobiology point of view, that's an absolute no-go. You could do this on the moon, you could do this in open space or so. You could sweat, you basically have this sublimation cooler with a human factory inside, so to say. You wouldn't be allowed to do this for Mars, and that's a big no-go for the red planet exploration, for example. Third problem, sizing. Those suits have to be really, really tight, adjusted to the very person who is wearing it. Now, the problem is, if you design such an MCP suit on Earth before going to Mars, and then you show on Mars 200 days later, after being 200 days in 0G, and no matter how well you train, your body shape will have changed, which means the suit which fitted perfectly on Earth will probably not fit on Mars anymore, which means you have to do the fitting on Mars. And that's a logistics effort as well. Fourth part is you still need a life support. I mean, you still have to have the air and the radio and the power, and you have the consumables, you have to get rid of the CO2 and so on and so forth. You still have to have the micrometeorite protection or the radiation protection from Mars, for example. So the idea is that from the outside, even if you're wearing an MCP suit, you wouldn't notice much of a difference from the local field as well. Plus, and that's the fifth problem, and that's a challenge out there which I think we have to put a lot of thought into, and that's contingency situation. Just imagine an astronaut is spraying an ankle on Mars. Getting somebody out of an MCP suit with a sprayed ankle where the astronaut is incapacitated, that's a challenge, and it would probably mean cutting open the spacesuit, which means you lose that particular part. So if you're not able to refurbish it on Mars, you lose the suit. And so that's that's a risk which I'm not sure how this is going to be handled or so. And that's the reason why most of the current other design systems are going for a more traditional approach with a hard upper torso, a mixture of what we saw during the Apollo times and a mixture of what modern technology enables us. Let's take a look at those ones, like here the Mark III, Mark IV suits here used with the Desert Rats. That's a NASA group which is working on Mars analog and Moon analog exploration projects with a geoscience focus, for example, also with human robotic interaction. And those suits, they look more elaborate. They also have their own cooling system already. They have radios on board, but they're not really meant yet to be this virtual assistant you might wish for when you go to Mars, for example. Now here's a look into the interior of those suits. Actually, this is the third picture of a so-called rear entry suit. You've seen those for the Russian Orioles. They have not been used yet for planetary surface exploration. They might go there. The idea is that if you have the suit attached to the outer hull of the space habitation module, and you open then the back plate, you can step right from the habitation module into the suit. You close the PLSS and you decouple from the habitat and you're already inside. You never touch the surface, which means you're not exposed to the dust. Now that looks very sexy, I know, and looks very promising, and there are a lot of concepts going in this direction. However, there come a few challenges with this. First of all, the mechanical strain on the airlock is tremendously high. The systems I've seen so far, I'm not sure how long they would survive in the Martian environment after repeated EVAs, for example. The second thing is, because of you're always carrying with you a part of the airlock, you have a mass penalty, and you also have a shift of the CG. The center of gravity is going upwards, which is changing the way your biomechanic works when you walk. Now, if you're on a flat surface, it doesn't matter. But if you're in a more challenging terrain, that can be a pretty limiting factor, and especially saying that the human is a very versatile machine which can go almost anywhere, changing that by lifting up the CG, that's probably not such a good idea. On the other hand, of course, again here, if somebody sprays an ankle, how do you get the person out? Getting out somebody for the rear entry suit who is incapacitated, that's pretty much challenging, which means you still would have to go for a classical airlock solution in addition. You might not use it as often. Yeah? So what I think we're going to is probably a combination of a rear entry suit system with a capability to go through a traditional airlock as well. There's not much happening right now on the Russian side. The suits which have been used, for example, for the Mars 500 study, where they had a 500 days isolation study, including a couple of days EVA sequence on a emulated Martian surface in a mock-up near Moscow, were basically Russian all-in suits with a few minor modifications, but they were, as I know from the people who've been working with those, it's not the most ergonomic system because it was never designed to be walked on the Martian surface. So this is not a system which is in development here, but was just modified from an existing pressurized version. On the NASA side, there are a few more things happening except for the Mark III, Mark IV system. The probably most well-known system worked on are the NASA SET-1 and SET-2 suits. Now the SET-1 is, you see a picture with it, it's also used to be called the Buzz Lightyear spacesuit because of the design with the bright green colors. It's a system which is a rear entry, as you can see obviously in the picture here. And the nice thing, it's ultra mobile. So the ergonomics point of view is really good. There are a lot of mobility studies on that, but they haven't worked on the life support system yet to that extent you would wish for. So right now, this is the first new system specifically designed for surface operation as a planetary mobility suit to be tested in full vacuum. It's based upon, the ergonomics is based upon 3D human laser scans, which was not available back in the Apollo times or so, lots of 3D printed hardware. From the materials point of view, in terms of impact resistance, the composites they're using, it's the most advanced system. It's certainly the most comfortable suit, which is also resizable, hard upper torso. So there's a few things where you really see a progression, but still a lot of things are challenging. You see a picture here of the current design of the SET-2 suits, and we hope to see them in action by the end of this year. They have electroluminescent patches on, so you have a lot of very easy way to identify them when they're far out in the extravehicular activity. They have superb mobility, although I'm sure they are still a long way to go to Mars. Another pressurized system, also in the United States, being worked on right now is the NDX-1 and NDX-2. ND stands for North Dakota State University. That's a group of Pablo de Leon. He was originally from Argentina and is now professor of aerospace engineering at the North Dakota State University. And he's gotten some NASA grants for working on a pressurized suit system. And it's a traditional suit with a hard upper torso system. They are still not very advanced in terms of the electronics inside, but from an ergonomics point of view and the mobility scheme, I think they're working at the 0.4 bar level or so. It's really a pretty superb system. It's also a rear entry system.